Hello, everyone. So this is the last live Q&A for MATH1055. I'm glad to see so many of you have joined. So before we start with the usual questions and problem solving, I would like to tell you a few things. So first of all, you might have seen this animation that was playing before the video. So that's something I'm going to have tomorrow. It's a live lecture. So if I just go back and show you. So this is going to be on my YouTube channel in live. And if you like planets, if you have liked the last part of the lecture with working with vectors and vector and scalar products, this is something for you. So it's going to be an elementary derivation of Kepler's laws. It's kind of a nice way of deriving the laws of planetary motion from Newton's universal law of gravity. So this is something, if this is something you are interested in, go and check out my YouTube channel. So as for some sort of housekeeping, there is this feedback form, end of term survey, I think it's called, that you can complete. So please do complete that form, that survey, and leave some feedback about your experience with this module, and it will help us to make things better and improve. So it is something that you will be benefiting from in the next term already. So please do complete that feedback form that you probably see when you log into Minerva. And finally, the exam is going to take place in January, and I think the timetables for exams have been published recently. So I believe I have seen the MATH1055 exam scheduled from the 18th of January at 2 p.m. So that means on the 18th of January, 2 p.m. sort of British time, you will receive the exam paper. I will probably send it to you via email, but I will make sure that it is available in various places. But you should get an email to your student email address at 2 p.m. on the 18th of January. But please do double check the date. I will also double check it and make sure that it's correct. So you will have 48 hours, that is 2 days, to complete to do the exam, and you will also have an additional 2 hours to upload the exam paper, your sort of worksheets to Gradescope. So I believe this is how it's going to be. So, and in preparation for the exam, you probably want to practice. So you might have seen my email sent earlier today saying that I put some sort of old exam papers up to Minerva. So do check these out. Do use them to practice. There are check sheets to go with them, so you can check if you got the correct answer. So this is something for extra practice. As I say in this warning, don't expect the January exam paper to be exactly the same thing. So let me see. So yes, probably if you have solved all the part B, all the problems in part B of the homework sheets, you should be fine. Okay, so don't stress too much on this exam. I mean, I know it a lot depends on it, and it's a sort of big chunk of your final score. It's something like 85%. So it is important. But if you are comfortable with all these things that we have done, you've looked at the problems, you practiced enough, you will be fine. You will have all the resources that you want. The module page will be up and running, and you will be able to use all these resources that I have given you during the term. So yeah, part B of the homework is kind of a good indicator. If you get those questions right, you should be able to do well in the exam. Okay. So as usual, if you have any questions, feel free to use the chat and ask your question. But let's just head over to item pool. So as usual, you can go to itempool.com/math1055/live, and let me begin accepting answers for this one. So it's a question related to complex numbers. It basically tells you to solve this equation: z squared equals the complex conjugate of z, and then plot these points, put these points in the complex plane, locate these solutions in the complex plane, and connect these different points. And it is asking what shape do you get. So Is it a circle of radius 3, a triangle built from 3 smaller triangles, a square with its diagonals drawn, or perhaps a line segment of length 4 units, that is. Okay, so do take your time solving this equation and locating the solutions in the complex plane, connecting them, and see what shape you get. Okay, so I see a handful of submissions already, which is good. So with these equations, with these complex equations, there are always at least 2 ways of solving them, or perhaps 3. So you might remember that we had seen that complex numbers can be given in various forms. So there was the algebraic form, which is x plus I times y. And then there was the polar form, which used, instead of the real and imaginary parts, it used the modulus and the argument of a number, that is the distance from the origin and the angle with the positive real axis. So depending which form of complex numbers you are using, equations might be easier to solve one way or another. So for example, in this, so here so here we have this equation, z squared equals the complex conjugate of z. It has basically products of complex numbers in it. By products, I mean the z squared thing part there. So it's kind of a good idea. It seems like a good idea to maybe use the exponential or the polar form of the complex number. But if you were to use the algebraic form, it's simple enough so you can solve it even in this x plus I y form. So there are several ways of going about solving it. I'll give you 2 more minutes, and then I'll finish this poll and show you the quick solution that I prefer. But I mean, there are, as I said, there are several ways of doing it. Okay, so just for people who have joined a bit late, we are doing the usual item pool quiz with this question right here. So head over to itempool.com/math1055/live and try to answer this question. If you don't have enough time to answer this one because I'm going to finish it soon, don't worry, you will get your chance for the next question. Okay, so there are like 30 something submissions. Okay, I'm going to finish the poll in a few seconds, so don't worry if you didn't get to submit your answer. So let's see. So the solution was the correct answer was option B, a triangle built from 3 smaller triangles. And since the answers you have submitted is pretty much, I would say, spread out and even, it's perhaps a good idea to look at this question. So here it's our equation. Z squared equals the complex conjugate of Z. So one way to do it is to write Z in its exponential form. So in the form that is r times e to the I theta, let's say. So here r is the distance from the origin. It's a non-negative number, and theta is a real number. It's the angle between the number connected to the origin and the positive real axis. And usually theta should be between -pi and pi radians, right? So if you write Z like this, then the left-hand side turns into r squared in multiplied by e to the 2I theta. So as you remember, taking powers of complex numbers raises the modulus to the same exponent. So squaring Z squares the modulus and doubles the angle. So the angle always gets multiplied by the exponent. And on the other side, so in order to get the complex conjugate of a number, all we have to do is to change the sign of its angle. So it's you might remember it means that you have to reflect the number about the real axis, and it basically means flipping the sign of the argument, the angle. So it's basically it has the same distance from the origin, but the angle has the opposite sign. In this case it's minus theta. So from this equation we can just simply take the moduli of both sides and compare them, and similarly compare these exponential parts. Okay, so this way we get two equations, and now let's just focus on the moduli. So now we have r squared equals r. So this has two solutions, this equation, because r could be 0. You might be thinking, okay, let's just divide by r, but first we have to make sure that r is not equal to 0. So let's think about what happens when r is equal to 0. Well, that's a solution. That's a good solution. And the other solution, so it's r is equal to 0, or if you divide by r and assume that it's not 0, then you get that r is equal to 1. So the modulus of our solution is either 0 or 1. Okay, so let's look at the other equation. So e to the minus I times theta is just 1 over e to the I theta. Okay, so that's just rewriting this negative exponent, this power with a negative exponent like so, the usual way. And then you can multiply both sides by e to the I theta. So what you will get is e to the 3 times I theta equals 1. Okay, so this is nothing but basically the usual equation for the roots of unity, the cube roots of unity. So we are looking for angles which, if multiplied, turn into well, 0 or some integer multiple of 2 pi, right? Because we want to end up at 1. So theta could be 0, or so that's one possible solution. E to the 0 is 1, or theta could be 2 pi over 3, right? Because if I multiply theta 2 pi over 3 by 3, I get 2 pi, and so e to the I 2 pi is equal to 1 again. Think of Euler's formula. Or theta could be minus 2 pi over 3. That's again a good valid solution in the interval minus pi to pi. So these are the three angles. So in summary, what we have for solutions is when the modulus is equal to 0, we get z equals 0. When the modulus is equal to 1, we have three possibilities. We could have 1 times e to the 0th power, so that's just 1, z equals 1. Then we could have e to the I times 2 pi over 3. And last solution is e to the minus I times 2 pi over 3. Okay, and if you plot these numbers, put these numbers in the complex plane, what you get is you have the number 1, you have these other two numbers at 120 and minus 120 degrees, and you have the origin. So this is e to the I times 2 pi over 3, and this is e to the minus I times 2 pi over 3. And this is 0. If you connect these points, you get an equilateral triangle. But if you connect all of them to the center point, you get 3 triangles making up a bigger triangle. Okay, so that's why it was option B. So how did I get minus 2 pi over 3? Yes, exactly. So Joseph already answered the question. So the idea is that you are looking for angles theta between minus pi and pi, so that triple that angle gives you an integer multiple of 2 pi. Okay, and an integer multiple of 2 pi could be minus 2 pi. Okay, all right, excellent. So I hope this was clear. I took perhaps a bit longer than I should have. I try to do it as setting, yes, z equals x plus I y. So could I show? Well, of course I could, but I'm afraid that if I do that, I will lose even more time. I'll tell you what, I'll work out that way, the problem that way, solve the problem that way, and I will upload a scan of my solution to the Teams channel, to the Teams chat, okay? So if that, I hope that's acceptable. So let's go to the next question, because I want to get through a few of these at least, so we have some extra practice. So again, go to item pool and answer the question, what does the following set look like when it's sketched in the complex plane? And here we have a set M consisting of complex numbers Z, such that the modulus of Z minus 1 minus 2i is equal to the modulus of Z minus 3 plus I. Okay, so it might look a bit difficult, but once you have seen the solution to this type of problem, you will always know what to do when you see a similar sort of condition or constraint on complex numbers. So our possibilities, the options we are given as possible answers are, is it perhaps a parabola or a circle or a hyperbola or maybe a line? Okay, so I see consistent answers. Now there's a new option appearing, well, a new submission. So think of this constraint that we have here. So z minus I minus z minus 1 minus 2i should have a modulus which is equal to z minus 3 plus I. Okay, so think of these, the left hand and right hand side of this equation, and try to turn this into sort of a geometric statement or condition on the location of these points Z. Okay, so again, this is something that might seem difficult if you. This is the kind of problem that might seem difficult when you first see it, but once you have seen the solution, you will, yeah, you will think, how did I not see that? Okay, so I give you another minute, and then I'll finish this poll. Okay, so let me finish the poll and see how you did. Okay, so the correct answer was option D. So it's a line, and it's not just any line, but let me show you what it is. So it's a very special line. So basically, you can write the question, the condition of Z like this. So what we had is Z minus 1 minus 2i and Z minus 3 plus I. I have rewritten what we are subtracting from Z. So in this way, so we are subtracting 1 plus 2i and 3 minus I from Z. And basically this distance, this modulus is the distance between Z and 1 plus 2i. This distance, this modulus, is a distance between Z and 3 minus I. So if you look at these two numbers in the complex plane, 1 plus 2i, so that's 1 plus 2i, and 3 minus I, these 2 points in the complex plane, then you see that the condition tells us that we are looking for complex numbers that are the same distance away from both of these numbers. So if I connect these 2 points, then you can immediately see that, of course, this line segment, the midpoint of this line segment, let me see if I can do it. So somewhere, this is like the midpoint. So this point corresponds to a complex number which is halfway between 1 plus 2i and 3 minus I. So this point, the complex number corresponding to this point, is certainly in the set M, but the point is that not just this one, but all of the points lying on the perpendicular bisector of this segment connecting our 2 numbers, all of these points are halfway between these 2 numbers. So this is our complex, this is the set of complex numbers we were looking for. Okay, so again, this type of condition, that whenever you see this, you should think of distances. So this is the distance between Z and I, 1 plus 2i. This is the distance between Z and 3 minus I. And if I want to find the points that are equally away from these 2 points, I'm looking at the perpendicular bisector of the segment connecting the 2 points. Okay, is that clear? Was that convincing enough? I hope it was. Now let me do a small tweak to this. So let me say that I do this. So now I have an inequality for these distances, and I'm looking for points that are further away from 3 minus I than they are from 1 plus 2I. Or I could say the other way, I'm looking for points that are closer to 1 plus 2I than they are to 3 minus I. So what do I get then? What do you think? Could someone tell us what we are getting in that case? What kind of shape, what kind of geometric object is our solution set? Yes, exactly. So it's a half plane above this line, and the reason that it is the half plane that is above the line is that we are looking for points that are closer to 1 plus 2I than they are to 3 minus I. So the perpendicular bisector is, of course, the midpoint, sort of the boundary between the 2 points. So along these lines, they are equally away from equally distance from 1 plus 2I and 3 minus I. If I move even the tiniest bit to the left of this line or upward, I will get closer to 1 plus 2I than 3 minus I. So all points in this half plane satisfy this inequality. Okay, even the boundary, because I allowed the equality to happen. Okay, so this is something you from now on, when you see a problem like this, you should be able to solve it right away. I hope this was useful and you liked it. Let me jump over this one. So the next one is about computing limits. So here we have a sequence 1 plus 1 over n raised to the 1 plus n plus first power, and we are looking for the limit of this sequence as n goes to infinity. Okay, so 1 plus 1 over n to the n plus 1 is the sequence that we are looking at. Again, just naively, you can't really tell what the limit is, just, you know, simply or naively applying these limit arithmetic, because what we have in the parentheses is 1 plus 1 over n, but that converges to 1 as n goes to infinity, but the exponent diverges to plus infinity. So we have something like 1 to the infinity. Well, that could be anything. That doesn't make a lot of sense necessarily. So, and as you will see, and you probably see that, well, some of you already see it, it's not 1 and it's not infinity. I can tell you that. The answer is not equal to 1 and it's not equal to infinity. Okay, I'll give you another minute before I close this poll. It's a simple limit, but of course you have to know a bit about special limits. Those are the kinds of limits like the nth root of n as n goes to infinity, or something like this one. It should remind you of a certain special limit that we had in the lectures. Indeed, it's a very famous limit. so let me finish this one as well. I mean, don't worry if you didn't get your answer in. I will show you the solution in a minute. Okay, so yes, it's E, Euler's number, and the base of the natural logarithm. And most of you got it right. There are a few wrong answers, but let me just show you how one can see this. So this was the limit that we were interested in, 1 plus 1 over n raised to the n plus first power, raised to n plus 1. So that can be, of course, written as 1 plus 1 over n to the n times another copy of 1 plus 1 over n. And then we could take the limit of this nth power and the limit of that last factor of 1 plus 1 over n separately. Okay, so of course, first we have to make sure that these sequences are convergent separately, but if you know a bit about these special limits, but of course, the second one clearly converges to 1, and the first one you have to sort of recognize or remember or look up in the lecture notes that it is indeed a convergent sequence and converges to E. So if you do this, apply this limit arithmetic rule that the limit of a product of convergent sequences is equal to the product of the limits of the convergent sequences that you are multiplying. So the first limit is E, and the second one is 1. So this is how we got E. Okay, Euler's number, which is approximately 2.71828128, and then it takes a different form. So let's. So what? There's a question: Is the infinite series of the same conditions also? I'm not sure if I understand this question. So there's something about an infinite series, but I'm not sure if I could. You please try to, or if someone else. Infinite. Ah, okay. So adding up these numbers, would it? Ah, okay. I see. I see. So as okay, that's a good question. Actually, I mean, we could have a quick look at that. So what if I took these numbers and add them up? So from, let's say, from n equals to 0 to infinity. Okay, so Adam already answered, said that this infinite series diverges to plus infinity, but could anyone tell us why? So I'm kind of curious to see if you can apply what we have learned so far. Yes, very good. So yes, so both of these answers are correct. So there was one suggestion that this infinite series fails the vanishing test. So we are adding up numbers of this form, 1 plus 1 over n to the n. So the terms in our infinite series does not converge to 0. Okay, they do converge to E, which is not 0. Okay, so basically you can immediately say, if you know this limit that it goes to E, this sequence, then you can immediately say that it fails the vanishing test, so it must be divergent. But as Adam has suggested, you could also say that each of these terms are greater than 1, so greater than or equal to 1. So this sum that we are looking at should be greater, well, should be greater than or equal to the sum where we are adding up infinitely many ones. Okay, and of course, if that doesn't diverge, I don't know what does. So it is a divergent series. You are adding up infinitely many ones. The nth partial sum is n, which does diverge to plus infinity as n goes to infinity. Okay, so that was a good question and good thing for us to look at. Now let me go to the next question, which is a geometric series. So we have the question, what is the sum of the following infinite series? And we have the sum as n goes from 1 to infinity of 1 over root 2 to the power n. Okay, and I've written out the first few terms. It's important that it starts with n equals 1, so the first power of 1 over root 2, not the zeros power, as you can see in the hint. So in the hint, I've given you the geometric series formula, giving you the sum of a convergent geometric series. But there, if you look carefully, you can see that capital N starts at 0, and little n up here starts at 1. So you have to correct for that, but if you do that, you should get the correct answer. Okay, I already see a good number of solutions with a big majority. It's reassuring, but don't worry if you get it wrong. This is the perfect place for getting things wrong, because we are here to learn from mistakes, and so that next time we'll be doing it right. Okay, so I'll finish the poll in a minute. Make sure you enter your answer. Okay, so let me close the poll. So the correct answer was 1 plus root 2, or 1 over root 2 minus 1. So there are different combinations of this number written as sort of the solutions up over there. So let me just quickly show you how I did it. So here is the infinite series that we are interested in. So if we had little n going from 0, this would be the sum, but that would include an additional term, an additional +1. So this sum includes the 0th term, so I have to subtract that. So I subtract 1, and then I take the denominator here and write this as √2 minus 1 over √2. I take that denominator over √2 upstairs, so I have this expression. Then to subtract 1, I just have to subtract √2 minus 1 over √2 minus 1. So that is what I'm doing here. So here I get 1 over √2 minus 1. So you could stop here, and this is a perfectly good answer. But if you don't like square roots in your denominator, you can get rid of that by basically multiplying it by this funny looking 1, that is √2 plus 1 over √2 plus 1, because this way you get a minus b times a plus b type of thing in the denominator. So that makes sure that you square this square root of 2 to get 2 minus 1 squared. So this is a minus b times a plus b, giving you a squared minus b squared. So in this case, a is equal to √2, b is equal to 1. So you get 2 minus 1 in the denominator. So the final answer is √2 plus 1. Okay. So I hope that was easy to follow. Do ask questions if something was unclear. Let me see. Yeah, I guess we could finish on this one. So the question after this one is just a usual calculate this vector product type of question. So that's the last part of the module, with dealing with vectors and such. But I think this question is kind of a bit more tricky, so it might be better for us to look at this one. So what is the radius of convergence for the following power series? And now we have an infinite series which involves some real variable x and powers of x. So we have the sum of k minus 1 over 3 to the power k plus 1 times x to the power k, with k going from 2 to infinity. And we are looking for the radius of convergence, basically what are the values of x for which this infinite this power series would converge. So the radius of convergence gives you an interval, gives you a radius around 0 on the number line, which if you take and stay within that radius with x, you are getting something that is sensible, a finite. You are getting a finite sum, finite number for this infinite series. And there is the hint telling you how to calculate the radius of convergence. You just take the kth term and the k plus first term, take their moduli and divide one by the other, and take the limit of this ratio of ck over ck plus 1. In this case, taking the modulus is not necessary, since we are dealing with positive terms. It would be important if it would be an alternating series or something like that. Okay. So I'll give you a minute or two, and then I'll close the poll. Okay, so let me just close the poll and then quickly discuss the answer. Sorry for being so quick with this. So the radius of convergence was equal to 3. So let me quickly show you why. So here is the kth and k plus first term. So it should be in the subscript. So here we have k minus 1 over 3 to the k plus 1 divided by k over 3 to the k plus 2. So this ratio of two terms can be written like this. Then we can simplify with k plus 1 many 3's, giving us 3 times k minus 1 over k. So this is the ratio of the consecutive terms, the kth term divided by the k plus first term, and this converges to 3. So this is the radius of convergence. If you take x in modulus to be less than 3, so x between 3 and minus 3, the power series will converge for these values of x. Okay. I have no idea why 0 was showing up with a blue sort of background. I have no clue. I will have a look later into that. So, but anyways, it was 3, and you could of course look at the edge cases. So what if x is equal to plus or minus 3? So for example, if x is equal to 3, the infinite series that we had looks like this. And here we had x to the power k. So in this case, x would be equal to 3. So here we would have basically k minus 1 divided by 3. We would be adding up numbers that do not converge to 0, so it would fail the vanishing test. So it would diverge in the case of x being equal to 3. And similarly, you can look at the case when x is equal to minus 3, and it would diverge as well. So if we are looking for values of x for which the power series converges, you have to stay in this open interval of minus 3 to 3. So my final question, all I would like to ask you is, which part of this module did you liked the most? Okay, so this is not an item pool question, it's just me being interested. If you have to go, that's fine. Thank you for attending, but if you have a minute or two, I would be interested in hearing which part of the module did you like the most. And yeah, so thank you for showing up. Thank you for being so great with these questions. Do take care, stay safe, have a good Christmas break, and prepare for your exams. You will be fine. Okay, see you.